Thank you everyone for joining this session. So session is about cooking with SQL, from ingredients to insight with manual preparation. So I'm Fabien Contaminard, and I'm here on stage with Serge Rielau. So he's the chief potato pillar, and I'm the pitch chef for this session. So Serge, tell me more about you.
Sure, yeah. So I've been doing SQL like forever, since I was like mid-20s, which was a long time ago. And I started off at IBM in the Alman Research Center, learning from like the co-inventors of SQL, and did 15 years at DB2 as SQL architect, short stint as chief architect at Open Pages, another 5 years Salesforce, and here I've been for 5 years now as well, and I'm what's lovingly called the SQL czar here, which means anything that happens on the SQL front goes through my desk. If it's SQL-centric features, I typically lead them, and if it's features that happen to have a SQL surface somehow, I consult. So that's me. Oh yeah, and I'm not allowed to cook in the kitchen at home, so this is the only chance I have is cooking.
So yeah, I'm a bit younger than Serge, but not that much. So I've been doing only SQL in my career. So this is what I say about me. I have one skill, it's SQL. So don't talk me about Spark AI. It's fantastic, but it's just not my skill set. Just previously, before joining Databricks, I was in Vertica. I was technical success manager. And before that, I've been in Teradata doing professional services. And actually, all those jobs requires a lot of SQL. And I've been working with Oracle database. I think the first version I came up with was like 7.3 something. And SQL Server, both Microsoft and Sybase, MySQL, PostgreSQL. And after, I had the chance to move to the MPP world with Greenplum, then Teradata and Vertica. Fantastic database. But now it's all about data intelligence platform, so the one on unique Databricks. So we have a bit of the menu à la table. This is the examples that we will cover today. So we try to stick around the theme of the cooking, and we'll see how you can optimize a Greek salad preparation. So this is a Greek salad optimizer. So let's say you have multiple ingredients to make a beautiful Greek salad. But to chop your ingredients, to keep your kitchen clean, you need sometimes in between ingredients. And actually, you want to be the most efficient possible. So you want to minimize the amount of time it will take for you to prepare this Greek salad. So to be able to handle this, we are creating like a table to get all the edges with the time that it takes to move from one ingredient to another. And we'll do a very naive algorithm that you will try every combination possible and just pick the fastest one. So basically, this is a data set. So we are creating a table. I have 6 ingredients that I self-join, just eliminating the same ingredients. And I put a random number as the time to preparation, just for, of course, for the demo. So this looks like this. This is just a symbol of the data set. And then we're building this query. So this is a new feature in Databricks. This is a recursive query. So basically, the upper part of the query is just selecting all the ingredients, getting them into an array to make sure that I know what ingredients I've been dealing with. And after, I'm going to union a new data set with a self-join from the recursive CTE just on a new ingredient that is not already in my list. And at the end, at the bottom of the query, I'm just selecting everything. So there is a where condition. I want to pick the recipe where I've run through all the ingredients, and I'm sorting them by the total time ascending, and we can just actually get to one. So let's see the demo with this. So it's the other way around. Yes, it's hard to click. Okay, so this is the same exact code that I've shown you in the slides. Of course, because there is some random numbers, probably you won't see exactly the the same values in the dataset. Don't worry, we'll get there. Okay, so this is the dataset. So this is an example. So if I'm already baking cucumbers and I want to bake tomatoes, to chop tomatoes, it takes 26 seconds just to clean the knife or something. I think you get the idea. And now we'll be running the recursive query. So this is exactly the code that I've shown you in the slides. So this is a previous run. But let's complete the query. So recursive query is, I was quite surprised when I joined Databricks that it wasn't there because it's been in other databases forever. And now we have the feature, so I'm very excited about it. And we see here, actually, we have two candidates for the fastest way to prepare your Greek salad. So we can use this order of ingredients or this one. Both takes 80 seconds to chop those. So yeah, so in my example, it was 76 seconds. So probably the random is close enough here. We'll go to see a bit more complicated example here now with a cake. Imagine I am a birthday cake company, and due to some reasons, I am limited in my egg supplies. I have only 250 eggs at my disposition. But this is a busy weekend, and I have lots of orders that if I want to fulfill them, I would need 5,000 eggs. So each cake are being unique here because those are birthday cake, and each cake, I can sell it for a certain price, and it also requires a certain amount of eggs. Let's just focus on the eggs. Let's say I have no issue with other ingredients, with the wheat, with the milk, and stuff. So actually, this problem is not that simple to solve. This is the 0-1 knapsack problem, which has multiple exact solutions. And to be fair, if you had to tackle this problem, the first thing you do will probably be the first algorithm here, which is called the glutton algorithm. Basically, you are sorting all your cakes by the division of the price by the number of eggs to have like the better candidates first. But when you fill up all your combination, it could be a good solution, but it could also be a bad solution. Usually, it's a good enough solution, but let's find out the exact solution. So usually, we solve that doing dynamic programming. So dynamic programming, maybe you saw that at school or in Kaggle or in somewhere. Usually, we saw this algorithm in C or Python or probably every language. And actually, I will show you how to solve this in SQL. So what we need for this? So we need a table that have all the information I need. So an ID, a name of the customer, because it's nice to ship the good cake to the good person, the price of this cake, and the number of eggs. I will use also for loops, so I'm using SQL scripting here, so another new feature that arrived recently in the platform, and just a SQL transformation command. So let's have a quick look at the data. So again, the sample, there is a lot of random. This is just to generate a sample. So of course the customer name here are a bit junky, but you have the price, you have the number of eggs. So that looks like this. So this is the glutton algorithm. So here basically I'm just selecting all the cakes. I'm ordering them by price/eggs in a descending order. So this is the window part of the order. And after, I'm taking the sum of price over the same window to find out the output. And also, I can aggregate the ID to know what cake should I bake. I'm ordering by the total price in the descending order because I want to have the best price. And here, my price on this example is 2,700 and some stuff. So So with dynamic programming, so it's a bit different approach. We are first building an array of 251 values. I first fill them up with a lot of zeros, just initialization of the algorithm. And after, I just parse one row at a time the component of my table. The order here does not matter. I have no order by clause here in the for loop. It has no incidence on the output of this algorithm. And here after, I'm transforming the array of values, and I'm replacing the zeros by the value of the price, only if the number of eggs is below the current number of eggs, or the price is better if the number of eggs is the same. So this is it. This is the code. And with this solution, I have close to 2,900 revenue. So let's run the demo. So just so you know, I'm showing you the code. I'm not running it because it's built with random functions, sometimes the glutton algorithm shows the best solution. But this is not the goal of this example. So we've pre-built the table, and I've made sure glutton algorithm is not the best solution. So this is the data set. So it's a bit different from the one from the slide because it's another table. So here we are running the glutton algorithm. So it's really a quite simple query. So on this new data set, the price here is 3,400 on some leftovers. And now we are running here the dynamic programming. So it takes a bit longer because we have to process the rows one at a time. So probably if you have like millions of possibilities, we should maybe rethink a bit the approach. But it will go to the end in 20, 30 seconds. And just at the end here, I'm selecting the last value of my array. So I have my array. In the array, I put the price and the list of the IDs of the cakes, and I'm updating them with the transform function with the case statement to make sure it's only a better fit at this time, and just looping over, and we have just to wait for the end. It will come along. Did some of you already run some dynamic programming, not necessarily in SQL, but in other language? Yeah, I have one here, one other here. So okay, so actually you're learning something. That's cool. So now I have my solution, and you see my solution is better than the glutton algorithm. So the other one was 3,400. This is 3,600. So by a small query and 20 seconds, we earn $200. And that's it for me.
All right. That was great. I just feel sorry for all these kids who don't get cake. All in the name of profit. Another way would have been to maybe optimize by the number of kids get happy. But hey, we are a business. So, all right. So the next problem we're going to solve is one of alphabet soup. And so here's our problem. So we are this fine dining restaurant, right? And we have international customers. They're coming from all over the world. Not everyone is named Smith and Jones. And we have international cuisine. Not everything is mash and burgers and the likes and French fries. So what we have discovered is that our staff has trouble finding guests when they come and they try to get a reserved table and they say their name, the staff types them in, and they can't find them for some reason. It causes a bit of confusion, people are complaining and stuff. So now we have talked to our tech support. There's probably some 15-year-old intern who's also working in the kitchen and who knows about computers. And he said the problem is one of collation. So these international guests, they have like all sorts of accents and other interesting characters in their names, and some of our cuisine is French-inspired or something Slavic, and comes with interesting names as well. So, and we need to actually go and update our database and make all these string columns, case insensitive as well as accent insensitive. Accents covering everything from accents to like other interesting, like German umlauts and so on and so forth. So what do we need for this? So I already mentioned collations. Collations is a feature that came in, I don't know, 6 months ago or something, and it's in public preview. And what this allows us is to customize the way how we sort and compare strings. So by default, Databricks collates everything in UTF-8 binary, which is basically just the Unicode code points. And that means all the lowercase characters are coming before the uppercase characters, and then after that eventually come all the French E's with all the different various squiggles above, and then come the German umlauts, and then come the Cyrillic characters, and it's all a big mess, right? So, and when you compare them, of course, an E with an accent aigu is not the same as a regular E, and so on and so forth. So what we need there is we need to actually go and teach Databricks to go and use a Unicode collation that is case insensitive and accent insensitive, which means that these things are the same. The other thing that we need is we are going to use dynamic SQL because what we're going to do is we're going to take strings and combine them, like glue them together, and then take the string and execute it as a statement, which is something that you would do all the time in Python with like spark.sql, you give it a string. But here we can do this within SQL, so we use SQL to build SQL to then execute it, okay? Lastly, we use the information schema, and the information schema is something that has been around for a long time. It is kind of like similar to describe and show, but describe is a problem that it gives you a fixed report. Information schema has the ability to give you just about metadata in a relational form, and you can then go and pick things out within SQL again, without having to resort to Python and the likes. So, and then we use SQL scripting. SQL scripting is a new feature that is in public preview just for a few weeks now, and Fabien already started using it in his cake example, and we're going to dive into this one in a bit more detail. So the formal name for SQL scripting is SQL/PSM. That is the name of the language in the ANSI standard. So it is a public, it's a standardized language, has been around for quite a while. Was originally, I think, designed by Jim Melton, who worked for Sybase at the time, and then ended up at Oracle. So, and the first ones who actually implemented it was probably my team, and I was an intern in 1996 in DB2. So, but it has been used. It's also used by MySQL. It is largely used by Teradata. It is very much so also Google SQL. They have done some smaller changes, but overall, it is something that has been getting more and more popular. So it's an open definition of a procedural language. Very similar to T-SQL and PL/SQL in the sense of like it's a different dialect. So all of that is SQL, but this is the formal standard we are following because we always want to be open. Okay, so inside of SQL PSM, the features you have is you have local variables, right, which is kind of like the basics. You have a compound statement. You can say begin and then put stuff inside. Local variables, you have the for loop. Fabien already used that one. You can also have loops, like generic forever loops, while, repeat, and then you can control the loops. You can exit out of a loop prematurely when you think you're done, or you can iterate by basically shortcutting to the end of the iteration and then repeating the next one. We have multiple ways of doing conditionals, so case statements, if then else statements, all the usual stuff, and we have condition handlers. So condition handlers are basically your try-catch. So you can say, hey, if I see this specific condition, this specific error message, then take this action and you handle the error, or you resignal and you pass it back up, right? And signal and resignal two-way scenarios, which means you can now do procedural logic without having to resort to Python, Java, Scala, or any other host language. If you're already a Python programmer and that's what you like, perfect, by all means, stick with it. If you're a SQL person who says, I don't really want to learn Python, now you have your way of doing that, and you can do it all in DB SQL in the warehouse, right, where you don't have access to these other languages. Okay, so just a quick overview of what's going to happen. We are going to first grab, we're going to loop through all the tables in a schema, right? We don't know how many we have. And we are going to grab the table names and then glue together a statement that changes, using an outer table statement that changes the collation for future columns to Unicode case insensitive, access insensitive. So that would be an outer table and then set the default collation. then we are going to iterate through all the columns within each of these tables and glue together alter table statements to alter the column collation that is for the existing columns. The default collation is for the future, and the next one is then for the existing columns. We're also going to collect all of these columns together into an array, all these columns into an array, because we want, after we have done that, we want to tell Delta to please run statistics so that we actually get statistics based on this new collation, which means things that were not the same before are now suddenly the same. It changes cardinalities and number of distinct values and so on and so forth, right? So, and then we're going to do this, as I said, for all the tables in our schema. And let me just go straight to the 3 fingers. There, okay. Let's hope we haven't lost the cluster in the meantime. So we're going to create, we have some standard, some simple thing. We have like someone with a German name, someone with a Slavic name, and an English name. And we have also a cuisine, like some German cuisine, some French cuisine, and some good Serbian chewabchi. What happened here? Why did I lose my own? One sec, for some reason, it got me out of the all screen. There you go. Okay, so we have done this. And when we run the query here and we're trying to find these users, these customers, they cannot be found, right? Because all we did was we had either the wrong casing, or we missed an umlaut, or we missed these other little accents. So now, let's look at the script here. So you see here there are some local variables, right? It's nothing very too exciting here. We set the collation Unicode access-sensitive, case-insensitive. Here we are doing our loop over the tables. We only want tables. We're not going to look at views. It would blow the example out of the water here. It makes it too big to also deal with views. And then we are going to glue together this alter table statement, right? And glue this together, execute it. So now this part is done. The future is safe. We have a nested for loop here, nested loop, and we are again finding all the columns now within that table that we're currently looking into, right? We want to find all the string columns. We do a set again. We glue together this string with the alter table statement, execute that, and then we're going to add the column that we found into an array to collect them all together. And then after this loop through all the columns, we're going to take a look and say, did we actually find any string columns? If there are no string columns, there's nothing to analyze, right? If there are string columns, then we run an analyze table statement. And for that, we're going to use a lambda function, which basically unnests the array into a comma-separated string with all the column names. And then execute that. Let's analyze. So let's see whether that works. Permission denied. How did that work? Still failing. That's what I select. Look, okay, I messed this. I need to do all these things. I'm not going to do this now. We don't have enough time. Okay, so what we should have gotten now is it would have changed these things, and then this is a previous run. I don't know. I was a different user then. And then it would give me all the 3 names properly. It would also order them properly, so the D goes before the M, goes before the S, and this particular D otherwise would be at the end. We went through this. Okay, so now the next one is we're going to make peanut butter jelly sandwiches. At least theoretically. Okay, so the problem that we have now is our kitchen helper, who probably was our IT support, is tasked to collect ingredients for orders, okay? And these orders, they can be in various places, right? The ingredients are stored depending on what they are. They might be in a bread box, they might be in the pantry, or they might be in the refrigerator. So we have different sources, different data sources, right? And occasionally what can happen is as we collate our stuff, we find out we don't have enough inventory. In this case, we have to basically put everything back, right? So we are going to make sure that this is a transactional thing. So what we'll need, we want to use temporary tables, our basket, so to speak, where we collate everything in, which collect trends and data within our session. We're going to use explicit transaction, aka multi-statement transactions, which can undo our actions if we fail halfway through. So we don't have to do a logical undo and like remember what we did, undo it. We can just go and just let the failure cascade, and it will just make it as if nothing ever happens. We're going to use the identifier clause, which is a more safer way to do dynamic SQL, it's more like parameterized SQL. I'm going to explain that. And then we're going to use that signal that we introduced earlier. So temporary tables are, at the end of the day, managed delta tables. Okay, so they have all the power that comes with delta, like, for example, liquid clustering. But they live in a session private schema. So they don't live in a schema that we defined in UC. There is a virtual schema called session, and that's where they live. And that is private to us, which means anyone else can create a table with the same name, and they will not collide with us. Also, if we have another session running the same scripts, again with the same name, they do not collide. Okay? And it's a great way to hold intermediate results. It's a great way to hold results that you want to then reuse multiple times and then later on clean up. So, and they are automatically dropped when the session ends. So you don't have to worry about cleanup. What if my session for some reason, you know, my session crashes or something else happens? I don't have to go and then mop it up and come up with unique names. So it takes care of itself. And the only thing you have to do is they create temporary. That's the only difference compared to a normal delta table. So that's the extent of it. Okay, the other thing, multi-statement transactions. So it's typically in Databricks, every statement is a transaction itself. So we auto-commit. You do an insert, commit it. You do a delete, commit it. Everything commits right away. And in this case, what we are doing is we're basically saying, when you say begin and you attach atomic to it, today we're just going to do that. It means everything in this compound statement will either live and die altogether, right? So, and the semantics for this are going to be repeatable read, which is if you are selecting from a table once and then you select from the same table again, you will get exactly the same result set throughout the duration of the transaction, unless, of course, you update the table yourself. So if your session updates something, you can see one changes, but you cannot see changes of others while the transaction is ongoing. So here's a comparison. So I do very simple. I just do an insert into t values 1, another one that gives me an error because it's a division by 0 error. On the left side, the first insert never happened. On the right side, the first insert happened, it committed, the second one failed, but the one is still there. Okay? So this is currently in private preview. As we progress through implementing this feature, we will eventually get to top-level begin work and then commit and rollback statements. So you can use this in Python and whatever to just run individual statement and control fully how these statements work. Okay, identifier clause is you have basically you take a string literal, but instead of turning a string literal into a SQL statement, you turn it into an identifier, which is a reference to an object. And you can do this pretty much anywhere in a query for tables, schemas, catalogs, catalog names, columns, even function name. You can write queries that have parameterized function names. Okay, here's an example. So you have declare v equals t and then select star from identifier v. And it will then substitute the v with t, resolve that, and then execute it. It's much safer than on the other side where you have execute immediate, right? Let me just stick with the slides in the interest of time. What we have here is we have our bread box, we have a fridge, we have a pantry, we fill in data, right? Including our recipe for the peanut butter sandwich, okay? So that's just set up. And then when you run it, we see here, so there's the temporary table that we created. It's begin atomic that says everything happens together. And then in here you see the use of identifier where we're basically using the query here to receive the location of where the item is, right? So if it says, oh, okay, so the strawberry jam is in the fridge, so therefore we get fridge as a result. We run the select over the fridge, and then if we don't have enough in our inventory, then we give a signal. Okay, we raise an error, and that then works like this. And if we can go, okay, let me see if I. Thank you. I give it a shot. Okay, there was our kids menu. Let me assume, in the interest of time, let me skip that part. We trusted that. Let me do the tempting. Permission denied, David. Still not. Something is not quite right. Okay. Okay, so we have this was what we did. So the idea is here we go now forward. We skip ahead. We have done a bunch of peanut butter jelly sandwiches. and we run low on strawberry jam, right? We only down to like 20 grams of strawberry jam. We are executing this again, and now we're getting an error, user raised exception, strawberry jam, right? We're out of strawberry jam. Okay, fine. Okay, so last step, prêt à manger. So we have done all these scripts, right? And they're complex, and things can go wrong, like we just saw. So ideally, we want to get into a situation where we have consistent quality, right? So if our line chef gets sick or something else happens, you want to make sure everything is always repeatable, right? So what we want to do is we write down our recipes and codify the execution. So for that, we need SQL procedures. And SQL procedures are written like this. So you have, they are in Unity catalog. They can have in, out, and in-out parameters. They can have result sets. They can contain any SQL script or SQL statement. You can grant access to them, so you can control who can refer to them. And you use a call statement to execute them. And here's a simple example. Create a procedure. This is the ... just the previous example. I'm going to show that in a moment. And then you call. Here, you see the create procedure. And we use today SQL Security Invoker, which means the invoker of the procedure is the one under which authority you execute, but we will change that in an upcoming drop and make it definers right, which means the definer can control what's happening inside. And then what you see here is we do an invocation, and if it works, it works. If it doesn't, then everything gets rolled back as before. And that is it. I apologize for demo problems. That's just what happens when you do live stuff.
Thank you.